Okay, well we'll talk about it. I can't promise you that every time we have a quiz I'm going to talk about the quiz, but since this was our first one, I'll talk about this. All right, so the first question here was to look at the graph of this function f and determine these limits. So the limit as x approaches -3, right? X approaches -3, and it's not specifying which side, right? It doesn't have a plus or a minus on the top right corner, which means you have to look both directions. So you go to your x value of -3, and you look from the left and the right. What is the y value? Approaching 2. Never gets there, right? But that doesn't matter. It's a limit. So this should be 2. And then the limit as x approaches +2 from the left side means, here's 2. Approach it from the left side. Your answer would be what? Where are you headed? -1. Approaching 2 from the right-hand side. Here's 2 from the right. You're headed up towards 3. And then the limit as you approach 2 without specification on left or right means you have to look both sides, right, which we just did. And in order for this to have an answer, what? These have to be the same number, and they're not, so does not exist. Not undefined, right? Does not exist. And then f of 2. This is college algebra now, so 1. That's it for the first one. Okay, on the next one, I do the opposite. I give you the information, ask you to graph, right? This is what we ended class with last time. So as x approaches -1, the limit needs to be 2. And I don't specify which side, right? Which means from both sides, we have to be headed towards 2. So I'm going to go to an x value of -1 right here. And I know that when I come in from the left and the right, I need to be approaching a y value of 2. So I'm going to just put a little dot here. I'm going to put some little tails off the side, and I'll figure out where those tails go after I'm done putting all the information together. All right, as I approach 3 from the left side, I need to be headed to infinity. So I go to an x value of 3. As I come in from the left, I need to head up to infinity. So I need to do something like this. And you could even put a little dot there if you want, like an asymptote. As I approach 3 from the right side, I need to be headed to a y value of 0. So from here, the right side, I need to be headed towards 0. So I could put an open and just pop it out the side like that. And then f of -1 needs to be 1. So that's algebra, right? There's a dot at -1. I need to put a y value of 1. So at -1, I need to be like this, solid. And f of 3 is undefined. So I'm just going to leave it like this. I'm not going to fill any dots in. Got that? The last thing is just to put this together. And the important thing is that when you finish drawing this, it needs to be a function. That means it needs to pass the vertical line test. At every point, I should be able to draw a vertical line and only hit your graph once, at the most. All right? So what I would do is out the left side, I just do whatever I want. It doesn't matter. Between here and here, I can just connect them. And then here, I'll just draw an arrow. It just keeps going that way. That would be acceptable. There's a few other variations you could have depending on, you know, how far down you came here and how far, or if you went up. Yes?
Is it all or nothing for that question?
No. There's partial credit on all of these. Yes?
What if we connected the one or the one with the B?
This one?
Yeah.
You connected it to what? This?
Yeah.
Well, then you wouldn't get full credit. You connected this right here to this?
Yeah.
And you didn't have it coming out this way?
Yeah.
You did not. So you did like this. Something like that?
Yeah.
Okay, so you tell me what's wrong with that. Do you see why that is not correct? Do you all see? Look at part A. You need the limit as x approaches -1 to be 2. And because there's not a plus or minus, that means it has to be the same from both sides. See, so here, what's actually happening when you do it this way is that your limit from the right, is 1. And the limit from the left is 2, and that means this limit would have to be, does not exist. Got it? So you would lose some points, not everything. Got this? We good? Okay. Yeah, the good news is that these aren't Scantron quizzes, they aren't Scantron tests. I'm always going to be able to tell, like, you know, if you deserve some partial credit. You always start out with full credit, and I just kind of take points off. All right? So everyone starts every quiz with 100. It's good news. All right, the last one was to see if you actually are going to do what I'm asking you to do in this class, which is to watch the videos that are preparing you for today's lecture before you come, right? The course videos. And honestly, how many of you actually did it? Okay, 1, 2, 3. Do you remember this? Didn't I put, it's 1.
But you explained something, and I don't remember, you said something about it.
But in the notes, didn't it say very important limits? 2 very important limits you're supposed to know. This was one of them. I didn't ask you the other one.
The question threw me off. Did you want to know why it is?
No, I wanted to know what it was equal to.
Okay, well then I got it.
Yeah, that's all I wanted to know.
I thought you were wanting to know why. You talked about it. And I can't remember what it is.
No, what is this limit? So that's all I wanted. 1.
You said what is this?
All right, so the moral of the story on number 3 is just continue to watch the videos. I don't want you to be sitting there watching them going, what's he going to ask me on a quiz through this? But I want you to be paying attention. If I say this is a very important formula, you should probably make a note of that, right? Okay. All right, this is the first quiz of many, so if you didn't do well, it's not the end of the world. But I hope that gives you some expectation, some understanding of what the expectation is here. We covered all this last class. You should be comfortable with it, and you should have some knowledge of what we're going to be doing today. All right, we're going to talk about calculating limits. Everything we've done up to this point has pretty much been graphical, right? I give you a picture and we talk about the limits, or I give you some limits and I ask you to draw a picture. Now what we want to do is we want to see if there's a way that we can evaluate a limit without having to draw the picture. So if I actually give you a function, is there a way that you can calculate the limit by hand, algebraically? And in 1.4, the section, the course videos, I go through and I explain that there are all these limit laws. Let me see if I can make this look a little better. I know you may not be able to read that, but I provide all this online, so I'm just assuming you could get to this. I say there's all these different rules, all right? And I go through and explain, like, and I know when I say it, it doesn't make a lot of sense, but when you see this in action, I think it'll be a little more cleared out in your mind. The big things that I want you to remember from these limit laws is that the ones that I guess we'll use the most is that the limit, I almost asked this on the quiz, but I remembered that there was too many formulas and this would maybe be a little too hard. The limit of a constant is a constant. So let me just give you an example of that. If I ask you what's the limit as x approaches 2 of the number 5? Your answer is 5. And the reason is because x does not appear in this expression. So if I'm asking you, how does x going to 2 affect the number 5? It has no effect on it, right? 5 is 5. So this answer would just be 5. And that's limit law 7. Now the next important one to note is the one right below it, and that's the limit as x approaches a of x equals a. So let me try and do it here like this, a specific example. Let me go to 3 this time. Let's say I want to know what happens as x approaches 3 of the function x, just x itself. So what do you think the answer is here? 3. Because you're saying, hey, what happens as x approaches 3 to the value of x? Right? If x is going to 3, then x is going to 3. That's it. There's nothing more to say. And then I'll do one more here. What's the limit as x approaches, let's say, 5 of 3x? You can. There is a limit law up here that allows you to take the 3 out, which is this one right here, limit law 3. But really, we don't even need to take the 3 out if we just think about it. If x is going to 5, if that's going to get closer and closer to a 5, 3 times 5 should be really close to 15, right? So it's what you think it would be. Everything I've done up here is kind of like, it's what you think would happen. None of these are really that interesting. But now what we're going to do is we're going to build up to more complicated problems where the thing in here is going to be kind of nasty. And when we try and plug in, you know, like x is to 3 or x is to 2 or x is to 5, something really bad happens. And we need to see if we can find a workaround. All right? All right, so these are the limit laws. I'll refer back to them if I need to. I think we're just going to get straight into some examples. Yeah, implied domains. I almost asked that on the quiz, but I decided not to. I just picked one problem out of here. I was going to ask about this implied domain thing, but yeah, that's a little complicated. I will point out this direct substitution property. You'll hear me say that. We're just going to do this with direct substitution. This is what I'm referring to. If you're looking at a polynomial function, a rational function, a trig function, exponential or logarithmic function, then if the x value that you're approaching, x is approaching 2, x is approaching 5, as long as the number you're approaching is in the implied domain of the function. The implied domain is the domain, all right? Sometimes people write out a function, they don't tell you what the domain is, but if you look at the function, you should know what it is. Like, check this one out. All right, this is a rational function, right? What is its implied domain? Everything except 2, right? That's the implied domain. All values of x except 2. So I don't need to write that down, it's implied. So when you're looking at a limit and you're trying to let x go to a number, the answer, okay, the answer is just plug that number into the function, as long as the number that you're plugging in is in the implied domain. So I'll illustrate that again with this right here. If I do limit as x approaches 1 of x over x minus 2, then this is a rational function. I should just be able to plug 1 in, and that's my answer, as long as 1 is in the implied domain. Is 1 in the implied domain? Yes, because this says everything except 2, so 1 is in there. So all I do is just plug 1 in. I get 1 over, what? -1, and the answer is -1. That's it. That's a direct substitution. There's no magic to this. Just plug the number in. You're allowed to do that, direct substitution, as long as that number was in the implied domain. Now, what would have caused a problem had I asked for what limit? Limit x approaches 2 of x over x minus 2. Now that you can't do a direct substitution, because if you do, what happens? This becomes what? I'm going to draw an arrow, not an equal sign. 2 over 0, that's undefined. The answer to this would not be undefined. We don't know yet. Okay, that's where we're headed. We're going to go and talk about that. What is this function doing? All right? All right, let's start grinding away at some examples. This is where we start to test your algebra skills a little bit. So let's start out with, now I'm going to use my phone, okay? I'm not breaking my own rules here, because I took a picture of a different textbook this morning, and I wanted to use some problems out of a different book, because I pretty much in the homework do most of the problems out of that section that you have for homework, 1-4. So I just decided I'd grab some other. Oh, there's a Pokemon. Hold on. Just kidding. So one of my students in my class this summer was like, it's not Pokemon, it's Pokemon. So, shit, sorry. Okay, we'll start out with this one. What is the limit as x approaches 1 of x over x squared minus x? Now, please keep in mind that if I wanted to, I could go and break out a graphing calculator, or I could break out, Wolfram Alpha? You've all heard of Wolfram Alpha?
Yeah.
Who's never heard of Wolfram Alpha? Oh, you need to go discover Wolfram Alpha. In fact, we should go discover it right now. Because Wolfram Alpha is something that used to not be there. In fact, it's one of my quick links, Wolfram Alpha. And I'm just going to type in, and it's a little tough to type these in, y equals x divided by, in parentheses, x squared minus x. Was that it? Yep. And I'm just going to hit enter, and Wolfram Alpha is going to do the rest. There we go. It just drew the graph for me. See that? Now I'm approaching, shoot, let's go somewhere else. Sorry, let's go 0. No, 0 is bad too. Let's go to, no, let's go to 4. Sorry, change that to a 4. I did not intend for it to be that bad initially.
What happened if it was a 1?
That we're gonna have to wait a couple of sections because you're gonna, yeah, just hang tight, hang tight. All right, so can you see from this graph about 4, we're here? Do you see that? So it looks like as we come in from the left and from the right, it looks like we have a limit. Do y'all see it? Yes? So we should get a numerical answer. Let's try it. What I'm trying to illustrate with this is that we could break out the graph, but we're trying to do everything here without the graph. We're trying to do it algebraically. Because at some point the graph is not, you can't rely on the graph, all right? All right, so we have a rational function, don't we? So we can try direct substitution as long as 4 is in the domain, in the implied domain. So is it? Should be. Let's just try plugging in, okay? I'm going to use an arrow, okay? I always like to use arrows first when I'm just trying direct substitution just to see what's happening. Okay, so what's happening? The numerator is headed to where? X, right? X is turning into 4, so that's just turning into a 4 over x squared. So 4 squared would be 16. Minus 4 again, so you get 4 over 12, 1/3. Yes? Was it 1/3 on that picture? Where did I left my mouse over there?
Yeah, it was kind of close.
It was above the x-axis, right? Yeah, it looked about 1/3. I can zoom in on this and stuff, but I think I have to pay to get the full features. But yeah, look right here at 4, 1/3 looks like it from left and right. Okay, so at least the math matches up, and that's great. But this is not a calculus problem. This is not an interesting calculus problem. What's more interesting is what's happening if I ask you if x goes to 0. So let's try that. What is the limit as x goes to 0 of this function? Okay, totally different question, right?
0 over 0.
Pardon?
0 over 0.
Yeah, we're going to get 0 over 0. Do y'all want to look at the graph again real quick? Just to see? What was happening at 0? Does it look like the limit exists to you? Does it look like as I come in from the left and I come in from the right that I'm headed somewhere? Yes. But if I try direct substitution, Just try the direct substitution real quick. That's why, again, I'm using the arrow. That means I'm going to do direct substitution. I get 0 over 0 minus 0. This is 0 over 0. And this, from now on, you'll see me write this a lot. This is bad. Okay? This is bad. This is why we're here. All right? Because it's obvious that the limit exists, right? I mean, from the graph, the limit exists. This number is not in the implied domain. I mean, yeah, it is not in the domain of this function, right? So I can't do direct substitution. I get some nonsense. And if you put 0 over 0 on your test or on your quiz, and that's your answer, it means you have no real idea of what's going on here. We're trying to get around this. We don't want this to happen. So how do we do it? At any time we run into a bad situation like this, anytime, we're going to have a couple of options on how to handle this. I'll summarize it like this. When we have a bad 0 over 0, we're going to do some algebra or a trick. There will be lots of tricks that I'll show you. When you see 0 over 0, realize that you're in for some work now. All right? Don't think it's over. Now, what was your name, sir?
Fred.
Fred? Okay, so Fred was asking, well, why not 1, right? Okay, because when we had 1, let's just look at what happens if we had put 1 in here. We would have got, the form we would have got here was 1 over 0, right? This is bad, but it's not this bad. We will not do algebra or a trick on this. We will do something different for this, all right? Stand by, that'll come in the next class or two. All we're focusing on today really is this situation. All right, so let's do this one. I've got the bad situation, I've got 0 over 0. So now I'm going to do some algebra. So I look over here, and I look at this rational function, and I realize that, what do I realize? What do you realize? Do you see anything here algebraically?
Yeah, I mean,
What? How about the fact that this factors? X squared minus x factors? You can pull out a GCF. And the GCF that you pull out is actually the same as the factor on the top. So I'm just going to I'm going to rewrite this problem. Watch, I'm going to write equals. So it's almost like you're starting over. This equals, I'm going to write the limit as x approaches 0. This is good mathematical penmanship to continue to write the limit the entire time. I will take off if you just all of a sudden drop the limit for no reason, then it reappears, and then you're just being lazy with it. You got to bring it with you until the very end. All right? So this equals this is x over x times x minus 1. Do you agree that's what would happen if I factor the bottom? Okay? Now, I am allowed to cancel those x's. Now this is something that may have slipped by in college algebra, so I want to be very clear on this. When we've done this sort of thing in college algebra where you had like x plus 2, x minus 4, over like x plus 2, and then x minus 7, let's say. Let's say you had some rational function, you factored, you got this, and then we always go, we get to cancel that, right? There was always a little asterisk that you had to have mentally when you did this. And that's, you're only allowed to cancel these if you promise me that x will never be negative 2. All right, that is not stressed a lot when you're in college algebra. You can only cancel factors if you guarantee me neither one of them will ever be 0. All right? So when I'm over here and I get the temptation right now to cancel these factors, I need you to now make sure that you're thinking about this. I can only cancel these if I promise you that x is never going to be what? 0. But I'm in a limit. And when I'm in a limit, am I letting x be 0? No, I'm letting x get close to 0 without actually getting there. So this cancellation is allowed. because you're promising me right now x can't be 0. Is this making sense, or should I clarify it a little more? Go ahead.
So if it was like x approaching 1 and we factored out that x?
That wouldn't matter. If this was x approaching 1, then canceling that wouldn't matter, because when x approaches 1, it's not even close to approaching 0, right? I don't know if this is getting through. I think it is, but I might be confusing you more than helping you. Hang tight. I'm going to write two functions up here on the board. And I want you to tell me whether or not they're the same or they're different. If I graph f and I graph g, are they going to look any different? What do y'all think? Identical? So,
Well,
plug in X or something.
I mean, assuming you don't add any values to that, right? Or what? To the x.
like, do we know what this one looks like? If I graph it? It's just a flat line going through the y value of 1, right? It goes like this. That's what f looks like. What does g look like? I'm going to do g down here. Give me a value. How about 1? Plug in 1. What do you get? 1 over 1, you get 1. Plug in 2. What do you get? 2 over 2, which is 1. Plug in 3. What do you get? 3 over 3, you get 1. Don't you? Yes?
Yeah.
So algebraically right now, x over x, I could just turn that into a 1, and then it would be f?
Yeah.
No. No, that's the point I'm trying to make. These functions are different. The difference is that you cannot plug 0 into this function. If I try, what do I get? 0 over 0, undefined. So the difference between these two functions is that when you graph this, it looks exactly like f, except at 0. You have a hole. Do you see the difference between the two? So if you're ever presented with this ratio and you cancel them, that's fine. Just make sure you promise me that you're not going to let x be 0. Because if you let x be 0, this would be undefined.
Would you ever get a negative value?
No. No, this is your input. Plug in -1 here. -1, you get -1 over -1 is +1. Plug in -2. -2 over -2 is +1, right? Okay, hopefully that clarifies it. If it doesn't, then just let it go. All right, so I'm about to cancel these two, right? There they go. I'm promising x won't be 0, but that's okay because the limit says I'm getting close to 0. How close? As close as I ever want to be without ever being 0. And when I do that, I'm left with equals limit again. I have to write it. X goes to 0. And what's left on top? You have to put that there, though, right? You still have a fraction. And on the bottom, x minus 1. And now, at this point, you have eliminated, look, you have eliminated the part that gave you 0 over 0, didn't you? You eliminated that. Now, tell me what happens when x gets really, really close to 0. If that's really, really close to 0, then this bottom is really, really close to what? -1. And 1 over -1 would be -1. Understand? So I can just put here equals 1 over -1, which equals -1. When did I stop writing the limit? When I actually substituted in the 0. And see, I hope someone's sitting there just saying, like going, look, you just told me I can't plug 0 in for x. And then on the next step, you plug 0 in for x. Right? I'm not plugging in 0. I'm plugging in an infinitesimally small number. So imagine that this number right here is 0.00000000000000000000001. Tiny number. -1. That's going to be a number that's really, really close to this, right? Yes? And when you do 1 over that, it's going to be really close to this. So we're talking about our answer, -1. We're not saying that it is -1. We're saying it's really close to -1. How close? As close as you ever want me to be. I can get there. I just have to move a little closer to 0, and I can get as close to this as I need to be. And if you go back to the graph, I think it'll confirm, that's not the graph, it will confirm what we just found. that as we're at 0, it looks like there's a dot there, right? There's actually a hole. The computer doesn't tell you there's a hole. Like if you were to graph that right there on your graphing calculator, you wouldn't see the hole that's there. But there is a hole. So as I come in from the left, it's approaching -1. When I come in from the right, it's approaching -1. Right? So it matches up with what I'm seeing graphically. Oh yeah. Oh yeah, we're going to do a different one.
So that was on the test, and someone put like -0.09.
That's wrong. That's wrong. Because the limit, this answer is telling you what it's approaching. It's not telling you, yeah, you're going to get to -1. It's saying as you get closer to 0, your function gets closer to -1. Not some other number. That number is the one it's getting closer to. Make sense? All right, let's do another example. Now this problem right here was just to get us to understand like what's going on. We need to actually start to see some real algebra. The algebra there wasn't that tough, right? Right, the algebra on that one wasn't that bad. All we had to do is factor a GCF. Limit x approaches 3 of 3 minus x over x squared minus 9. I'm going to do this problem without the graph. I'm not even going to look at the graph until maybe we're done. All right? First thing I want to do is just try direct substitution and see what happens. Let x become 3. 3 minus 3 on top gives me 0. At that point in time, I don't know if that's bad or not. Okay? I still need to figure out what's happening on the bottom. But 3 squared minus 9, right?
3 squared is 9. And
9, 0. So we get 0 over 0. This is bad. So I'm going to do either some algebra or I'm going to do some tricks. I haven't shown you any tricks yet. All right? We'll get to it. Right now, just going to do some algebra. So what algebra am I going to do? Yeah, so you should just look at x squared minus 9 and be like, yeah, it's different squares, obviously. So let's try that. Limit x approaches 3, so this equals this. And it factors to be x plus 3, x minus 3. I'm hoping that I can get rid of the 0 over 0 problem that I have. Can I yet? Yeah, good. Almost, right? These almost match. 3 minus x almost matches x minus 3. They're off by a sign. So the standard way to remedy that is to factor a -1 out of either this factor or this factor. It's your call. Does everyone see that? They're off by a sign. +3, -3, negative x, positive x. If they're off by a sign, you can factor -1 out. What about these two? They're not off by a sign. Look, +3, what? +3. Those are fine. Negative and positive. Those, you have to have both of the terms be off by a sign, not just one of them. So limit x approaches 3. The top, if I pull a -1 out,
So the x minus 3?
I can write it as x minus 3. Everyone agree? If you don't believe it, just distribute through and you would get back this and just rearrange it. And then what were you saying? We can what?
Then factor out the x minus 3 is
You can cancel these factors, reduce this, as long as you're promising me that x is never going to be 3, right? Because that would make these 0. But I'm in a limit, right? I'm in a limit, so that's okay. Gone, gone, equals, do I drop the limit yet?
No.
Nope.
There's still like your x plus 3.
Yep, I'm still got that. I'm just going to rewrite it. -1 over x plus 3. And now we can drop the limit, yes, because we're not going to have a problem. Good. So -1 over 6. And we got a nice number. Do y'all want to see the graph? This will probably be the last graph I look at because it takes up too much time. I'll go back to Wolfram Alpha, and I'll ask it to graph y equals 3 minus x over x squared minus 9. And it's going to tell me, I think I have the pro account on this, but
How much is it? Do you know?
oh, Wolfram Alpha is free. Oh, the pro account, I have no idea. I have no idea. Wolfram Alpha, the company Wolfram, is the same as the company that makes this program, which is where I do all the notes. And I could graph everything through this program also, but Wolfram Alpha's brains is this program, which is called Mathematica, Wolfram Mathematica. So I guess what I'm getting at, if you're really interested in like programming and doing some really cool stuff that's even more powerful than Wolfram Alpha, is to go buy the program Mathematica and learn how to use it, because it's pretty awesome. Look, if I want to graph something, I'm not going to do it because it's going to have to go back to my keyboard. I can just come over here, and I know this looks crazy complicated, but where are my graphs?
So how much does Wolfram pay?
For a student version, it's pretty cheap. It's about $150 for a student. Okay, so if I want to do it, that's as much as a calculator.
No, I'm saying
I know.
they pay you. You're promoting them. I asked how much they pay you.
Oh, they don't pay me. I've been using this. Look, this is Wolfram Mathematica 10.0. I've been using it since 3.1. When I was a student is when I first got it. So, I mean, it's just super powerful, the things you can do in this program. This is what I use for my Cal 3, all my animations, all my three-dimensional stuff, rotations. It's all using this. So if I want to do a two-dimensional plot, I just click on this and it'll bring it up. I just type in the function and I can make it different colors, and it's really cool, really user-friendly. Okay, sorry, let's get back to this. Where's the graph? It didn't graph it? Oh, I guess it's, oh, I need the pro for it to graph it. That's pretty bad. That sucks. Okay, well look, I think we're just going to have to trust our answer. I trust it. It's right. Yeah, there's nothing messy in that problem. All right, you ready? Moving on. We turn the screws. I know some of you have had me before for other classes. Do you remember me saying turn the screws?
No, I think this is the first.
First time? Okay, well, the term turn the screws, does anyone know where that comes from, that phrase? No? There used to be a torture device back in the medieval times where they put people and they try to get them to confess, or they're just punishing them for believing something different than whoever was punishing them believed. And you know, they put their head in like a vice and they start turning it and tightening it up, right? And come on, you know, say you believe in whatever, or tell us the truth or something. And they didn't, they turned the screws just a little bit, and you just keep turning the screws and more pressure, right? That's the term I'm using here. So we're going to continue to turn the screws and we're going to apply more pressure. The problems are going to get harder, the algebra is going to get more challenging, right? But I'll try and turn slowly. We can just back it off completely, right? All right, limit. X approaches 3. Look, you can blame Isaac Newton for this. Don't blame me. I'm just the messenger. Try your direct substitution first. There's a habit that students get into. They're in a calculus class. They're taking a test. They're under pressure. They get this right here, and all of a sudden, they just assume it's bad. They assume it's 0 over 0. And they forget, just try direct substitution. It may turn out to just be like the answer to this is 4. Done. And Is it? Let me see. Let's see what happens with direct substitution. What do we have? 9 minus 3 minus 6 on top?
That would be 0.
That's 0. So we're halfway to bad. And then 9 minus 15 plus 6. We are fully to bad. All right? We are 0 over 0. And this is bad. But what I'm getting at is that if this turned out to be, let's just say, 0 over 2, what would that mean? Your answer would be 0. 0 divided by 2 is 0, right? So you'd be done, and there would be nothing else for you to look at. So you always want to check this first. Since it is a bad situation, though, I'm going to have to do some sort of algebra. And up to this point, what has been our pill that we've been able to use that's fixed the problem every single time so far? Factoring, right? So, yes, we told you back in college algebra this would never go away. You must be able to factor a quadratic trinomial, and it can't take you 15 minutes anymore, right? It's got to be pretty quick. So,
Let's see. Numerator will be x minus 3x plus 3. Actually, no.
X equals 3x minus 2.
x
And then
plus, what, hold on, let's make sure we're all good with this. Minus 3 plus 2?
Yeah.
We all agree? Okay, bottom?
x minus 3, x minus 2.
Minus 3 minus 2?
Minus 6.
No, minus plus 6 minus.
Well, you got to get your brains going again.
It can work again because like it's
This
x
is-
minus
this is
1
correct.
minus 6. That's actually another trick that works too.
X squared,
Works other way.
negative 2x, negative 3x, that's negative 5x, negative 3 times negative 2, positive 6.
Works same way.
This is a good problem because a lot of times when we see this, we want to use like negative 6 and positive 1. But it's not. All right, do you see what's going to happen? We have common factors. We can cancel them as long as we promise x is not 3. It's not. Am I going to drop the limit? Not yet. I'm just going to rewrite it. Oh my goodness, what time is it? X minus 2. I need to speed it up.
And then we can drop the limit.
Now we can drop the limit. We should be able to direct substitute. What is that?
5 over 1?
1? Answer is 5.
If we forget to drop the limit there, you can
Like if you were to write the limit again and the limit again, it wouldn't be wrong, but it would be, I don't know. I would be wrong to not tell you that you need to fix that. If I just said, yeah, keep doing that, that would be incorrect because then someone else later on the road would be like, why do you always have your limit there? And you'll be like, well, 'cause my Cal 1 instructor said just didn't matter. So, yeah, it would be bad notation. It would be bad notation. The rule is you drop the limit as soon as you actually go in and replace x. When you go in and replace x, the limit is gone. But until you do that, it's with you the whole time. All right, and we keep going. So I guess you need to be able to factor in order to do this, right? X goes to 0. 1 over x plus 3 minus 1 over 3 over x. So now we're starting to get into some more complicated looking things. We have here what we would refer to as a complex fraction. It's a fraction with fractions, right? Mixed in. Let's try direct substitution. What would you get with direct substitution?
0 over 0.
Get 1/3 here, right? 1/3, take away 1/3 over 0. And 1/3 minus 1/3 is 0.
So it's bad.
So it's bad. You don't have to write bad down, okay? I like to write it though. It's bad. Whatever works for you. I've always done it when I'm showing you.
-2, you didn't put that.
I didn't what?
I said -2, you didn't put that on the test.
Oh, yeah. Start taking off. All right, well, factoring has saved us up to this point, right? There's no factoring that you're going to be able to do to this.
So they gotta do a trick.
So some sort of trick or some algebra. It's still algebra. I'm not quite sure I want to put it into the category of trick yet. There's stuff that truly seems like trick later. Got to try something.
You gotta do the top.
Multiply by x or 3. We could try a lot of different things because it's algebra and there's all sorts of things you can do to manipulate something algebraically. So all of those sound like they might be valid, but I'm going to tell you what the standard technique will be that you can always go to and try. If you have a complex fraction, you're getting 0 over 0, try and bring the two fractions here together into a single fraction. So you want to combine those two, which means you need a common denominator. So we're going to try and put these two fractions together into a single fraction. So the algebra technique here is not factoring, it's combining two fractions together, getting alike denominators. So what would you have to do, what would your denominator need to be that would be a common denominator between these two? 3 times x plus 3, right? So we need to get, we can call it an LCD if you want. It should be 3 and then x plus 3. I need both denominators to have that in it. This one right here is missing a what? A 3. So I'm going to introduce a 3 down here. And when I do that, I multiply the top by 3 at the same time. 3 over 3. Why do I do 3 over 3? Because 3 over 3 is 1. And 1 times anything is the same thing. So I'm not changing the problem, I'm just changing the way it looks. How about over here? What am I going to introduce? X plus 3 on the bottom, and on the top, x plus 3. Now this is stuff you did in college algebra, combining two rational expressions together. Pardon me?
We totally just cross multiplied.
How do you mean? Oh, you just like put the 3 up here and the x plus 3 up here and then you put them together?
Yeah.
That's fine.
I find that.
Whatever you want, but don't call it cross multiplying. Just, call it something else. Because cross multiplying, you technically need an equation to do cross multiplication. You need an equal sign. That's what cross multiplication is. But okay, it's all the same. You need to be able to put those two fractions together, period. All right, I don't care how you do it right. All right, so next thing. Limit x goes to 0. I'm going to have 3 minus x plus 3 over 3 times x plus 3 over x. And notice that I used different size division bars there. That wasn't just for fun. It's because my main division is here, right? And when I put these two together, I created another division bar, but this one, whoa, that was kind of cool, right? It's touch screen. Hold on.
Yeah, it's kind of clear. Yeah, it's kind of clear.
I need to take whatever the hell that iCloud thing is out. All right. Are y'all okay on me putting the numerators together? 3 minus that, right? I left it in parentheses because that negative must distribute through. Right? That negative has to go to both. So I'm going to do that on the next line. 3 minus x minus 3 over 3 times x plus 3. All of that over x. And I think what I'm going to do here, to help you see why that big division bar is so important, is I'm going to put x over 1. And I think what that creates is a little more balance in what you're looking at. You have a fraction over a fraction, right? That's what this is, fraction over fraction. Now something good should happen, right? We started with bad, At the end of all this, something good should happen. So let's see if something good does happen. Do you see anything? Look at the numerator. Look at this numerator. 3 minus 3, 0, right? Okay. So this 3 minus 3 is 0. So we get limit x approaches 0. What do we still have on top there? Negative x over 3 times x plus 3. But all of that still over x over 1. And do you see what's about to happen? No? A fraction divided by a fraction is equivalent to a fraction times the reciprocal, right? So what I'm going to do is instead of having x over 1 on the bottom, I'm going to rewrite this over here. And am I going to continue to write the limit? Yeah, I'm going to continue to write the limit. Limit x goes to 0. I'm going to write it as negative x over 3 times x plus 3 times what? 1 over x. So I'm basically flipping it and it's coming up. That's why I think it's important for you to write this as x over 1 so you can see the fraction getting flipped. 1 over x. Now what?
-1.
Yes, the x's are going to cancel, right? These x's are going to reduce out. As long as you promise me that x what? Is not 0, but I'm in a limit, so it's okay to do this. And that right there, that step right there, is what took away the 0 over 0. The bad situation was just eliminated. We need to finish up, though. We're not done. Were there any questions, though? Limit x goes to 0. What do we still have on top?
-1.
-1.
3 times x plus 3. Something like that. Oh.
Why is it -1?
Because it was negative x, wasn't it?
Oh, okay, okay.
So the negative still stayed there. The x just kind of went away. At this point, direct substitution should take care of it. Try and plug in your 0 now. It's not going to be a problem, is it? -1 over 3 times, what's 0 plus 3? 3?
Oh, yeah.
So 3 times 3? -1/9. The function is headed to -1/9. Got it? Common denominators. What time did we go to? 12:40?
Yeah, we got like 4
Okay, good, good. We need all that time. All right. Shall we? Yeah, we're going to continue. I don't even know why I'm asking you. Should we continue? Do you remember I was telling you how Cal 2 is a lot harder because the concepts are harder, but it's also much faster paced? I mean, it is seriously much faster than this. I'm trying to go, it's our first day of real lecture today, so trying to keep it at a good pace for you here, but the reality is that you have a lot of work to do tonight. All right, here we go. In an effort to save some time, I'll just tell you that is bad, 0 over 0, all right? You could check it, it's bad. Factoring doesn't look like an option because I don't see squares, I don't see polynomials. The fraction, getting the common denominator that we just used, I don't see that either because I don't see complex fractions, right? I don't see fraction within fractions. What I do see, though, is a radical. We always like to square things, right, to get rid of radicals? There's a problem with that, though. The problem is this. It's kind of like if I just write the number 4 down, that's 4, right? If I just come in here and square it, is it 4 anymore? It's not. It's 16. So if I have this expression and I just come in here and start squaring things, it's no longer what it started as. The times that you're allowed to square things is if you had an equation. Now, if I have an equation, I'm allowed to square both sides of the equation, right? And that's because if I ever need to get back to x, I know I could, I'm not saying that I'm not saying anymore that x is equal to 16. I'm saying x squared is equal to 16. So I'm maintaining the relationship I have there. Big story is you can't square it. Okay? It's an expression. You can't just square an expression. It's no longer the same expression. Anybody else remember anything that you did with radicals? Pardon?
Something with a fraction in the exponent.
Yeah, you can rewrite that as a fractional exponent. We'll do that later, but that's not how we're going to do this. I'm just seeing if anyone recalls something with radicals. There's no?
Is it multiplying the top and the bottom by that?
Yes, by what?
The x plus 1 or conjugate?
There you go. Okay, good. The conjugate. Y'all remember the thing called the conjugate? Okay. So, you hated that? All right, well. Welcome back. All right, I'm going to, anytime we see this radical like this, radical and then we have minus a number or plus a number, doesn't matter. We know this is a bad situation, 0 over 0. We are going to introduce what is called the conjugate. You can go and look it up if you want, but I can just tell you what it is. It is going to be a 1, okay? I'm about to put a 1 there, all right? But the 1 that I'm going to put there is very special. It's going to be exactly what I see right here, root x plus 1, but instead of minus 2, I'm going to put plus 2. And then on the bottom, I have to do the exact same thing. I only change the sign between the two things. Between the radical and the 2, I just change that sign. This was minus, I just write plus. Plus. That over itself should be 1, shouldn't it? So I'm not changing the problem. I'm being clever. This is almost like a trick, but you've probably seen it before, the conjugate thing. Now, what does the conjugate actually give us? Let me show you real quick over here. Let's say I have something minus this, all right? And I just come in here, I'll write it as a fraction, and I just come in here and I decide to multiply it by its conjugate, which would be a plus b over a plus b, right? So here I have an expression. Here's its conjugate. Doesn't have to have radicals. You probably thought it had to have a radical to be a conjugate, but it can be pretty much anything. So if I multiply these two together, what happens? This, 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 and what goes away? The middles, right? The middles. And what you wind up with is that first one, a squared, right? And this last one, b squared, but subtracted. And why is that valuable? Because if we look at this right here, this is like our a, right, minus our b. At the end of it all, the radical won't be there. Because the only thing that's going to come out is a squared, which will be the radical squared. So no more radicals. That's just to show you why we do it. But let's actually go through and do the work now. Okay, I want to.
The way of squaring without squaring it.
Yes, but here's what you give up. You introduce this nasty thing down here, right? You're going to get rid of the root up here, but you're going to have a root down here. So that's the give and the take. But it turns out this isn't going to hurt us. It's actually going to not matter. No, no. We get lucky the way things work. All right, let's try the multiplication out. I'm also going to put a parentheses around this because this is 2 terms, right? And then right here, this is 2 terms like that. So I'm going to make sure I'm clear that where everything's separated. All right, let's do this multiplication. Root x plus 1 times root x plus 1. The roots just go away. We just get x plus 1. Now, on the next multiplication, from here to here, I did it in red because I don't even care what it is. Why don't I care? Because I know it's going to cancel out with that one right there. That's guaranteed. So the only thing I really need to look at is this last multiplication, which is this to this. Negative 4. Minus 4. Got it? That's all that's on top. Notice my limits in here. I didn't lose it. Over. Now on the bottom, your temptation is going to be to multiply it out, right? That's going to be your temptation. Don't. The reason why